Feel free to ask your neighbor. Many of you do have the right answer. You can eliminate some answers by asking yourself, is this going to be a positive or a negative potential? Which charge will dominate? Both charges are the same distance from the point. So which charge will dominate? Positive or negative? We'll stop in about 10 seconds. Stop at 2:15. Just guess if you're not sure. All right, going away. Hey, I think that's pretty good. So we start with this. V equals KQ over R. Do the sum of them. The sum of the potentials is going to be K. I'm just going to put in 2Q here. You might have done it a little bit differently. Over 1 meter minus K 4Q over 1 meter. And then I can simplify this and just say it's negative K 2Q over 1 meter. You see how I did that? I just said 4Q and negative 4Q and 2Q is, or it should be negative 2Q. And so that's going to be 9 times 10 to the 9th times 2 times each charge is 2 microcoulombs, so that's 2 times 10 to the minus 6 divided by 1. So that's 36 times 10 to the third. It should be a negative here. So it's negative 36,000. But as I mentioned, or as I sort of led you to believe, is that since our negative charge is a bigger charge, and it's the same distance as the positive charge, it's going to impact the potential more at that point. I'll have 36,000 joules per coulomb, or volts, at the point above those two charges. All right? As far as the future, you'll probably never see the potential due to a point charge again unless you take the MCAT or whatever. But the idea of potential is important to everybody. I mean, you know, we use wall outlets, and many of you going into the health sciences will see it again elsewhere, either in instruments or in the body, where the body, you know, there's a lot of electrical stuff going on in the body as well. All right, one more thing. So we have electric forces, electric fields, force per charge, electric potential, energy per charge, and now we're going to sort of tack on energy as well. The electric potential energy. So, as we said before, actually before we do that, let's do a few clicker questions, sort of stay on track. Where did we leave off? We did some of these, did we? Is that right? No. We're about to do it. I'm going to just do it. Isn't that what we say? Or we might just do it, I guess. Do y'all have any idea what I'm talking about? I'm just going to do it. I'm going to just do it. Y'all never heard that before? Man, I thought that I was going to connect with you. But I see that you're behind the times. It's because you're all a bunch of biology majors. And you're lame-o. No, you're not lame. All right. A proton and an electron are a constant electric field created by oppositely charged plates. You release the proton from the positive side and the electron from the negative side. Which feels the larger electric force? So these are two charged plates, one positive, one negative. You release the proton here, the electron here. Which feels the larger force? Free to ask your neighbor, and we'll stop in about 7 seconds at 52. Okay, I think that's right. Yeah, they feel the same magnitude force but opposite direction. You can think of this, they're both in the same electric field, right? The electric field here is the same as it is over here. Because when I have these two parallel plates, the electric field lines run parallel to one another. All right. And remember, the electric field, the magnitude of the electric field is given by the density of the electric field line. So if our electric field lines were closer over here, that would mean a bigger electric field. But they both feel the same electric field, so they both feel the same force. It's also important they both have the same charge. Right? A proton and an electron both have that fundamental unit of charge, 1 each. A proton and electron are in a constant electric field, yada yada, same as you had before. Which has the larger acceleration? Same scenario, which has the larger acceleration? Proton or electron or one of these other things? The same, no acceleration. All right, we'll stop at 35. Hey, awesome. Why does the electron feel the larger acceleration? Tiny little mass. It's like 1/10,000th the mass of the proton. Do you know that? The proton is like 10,000 times the mass of the electron. I want to joke. I don't know. Have you even had one today? Oh yeah, that was not a very good one. This is a good one. You ready? What did the janitor say when he jumped out of the closet? Supplies. My mom used to be a janitor at a skating rink. And man, as a kid, that is like the best thing in the entire world because I got to spend the whole summer at the skating rink. And she would also run the snack bar so I could make the cotton candy. And I could make those sodas that we used to drink where you put like 12 different kinds of soda in a cup. We used to call them the suicide. Man. But she never did that. She never yelled supplies. All right, the electron because it has a smaller mass. Which one has more kinetic energy? Think about this. I already said a couple of things, but which one has more kinetic energy when it strikes the opposite plate? Same scenario as we had before. Which has more kinetic energy? All right, I'm going to stop at 40. 40? Just guess if you're not sure. Ask your neighbor. They're doing pretty well. Okay, very good. They both require the same energy. A few of you put E. E is they acquire the same energy but with different signs. Kinetic energy doesn't really have a sign. I don't remember from last semester. As far as you have that V squared thing, you can think of that as taking away a sign, but really it's just that it's scalar. But you know, work was a scalar quantity too, and it had signs, so I like to think of it as V squared, that takes away any sign information. And then some of you put proton, you're thinking, oh, it has a bigger mass. That's okay, but that's wrong. Some of you put electron, you think, oh, it has a small mass, but it has such a big speed, right? And V is squared, so therefore it must have more energy. And that's good thinking, but it's not really correct. They're both going to have the same amount of energy as they move through this electric field. They're crossing the same potential difference, right? And remember that potential, V, is equal to energy over charge. So if they have the same charge crossing over this potential, they're going to both gain the same energy. This basic definition tells us that they both have the same energy because they have the same Q and they have the same V. We'll come back to this. Now let's look at electric potential energy. How y'all feeling on this? Sometimes students have a little bit of trouble with it. It's kind of far out there. Yeah? Yeah? Nobody does this, right? Yeah.
bear with it, okay? Forces, fields, forces we usually get okay, but fields and potential can be really difficult for students. In fact, it might even be the hardest chapter that we take all semester. We get into some other chapters later with circuits, and they can get a little hairy, but as a concept, the fields and potential can be kind of difficult for students. So just do the reading, take a big deep breath, do the homework, practice these things, practice, it'll help you a lot. All right, let's look at electric potential energy. Not potential, this is potential energy, but let's go back to our potential. Remember we said the potential due to a point charge is K Q1 over R. Let me see something. Don't turn the page. I just want to see something. Okay. So I have this written on the next page. But what I want to do is I want to bring a second charge, Q2, from very far away. And when a charge is really far away, this is one of our reference points, or this is our reference point. When I have a charge that's really far away, what is the potential at this point due to that charge over there? If R gets really, really, really big, what is V? 0. So if R goes to infinity, V goes to 0. That's sort of our reference point. So imagine I have this charge over here. It's unaffected by that charge. The potential is 0 at this point due to that charge over there. And what I want to know is how much work does it take to move this charge and put it right here? And whatever work is required will be equal to the potential energy of that configuration of charges. Anytime I have two charges, two or more charges, they have energy, whether they're positive, negative, or both. They have energy because if I let them go, what's going to happen to these two charges? I'm holding two positive charges right here. What's happened when I let them go? Watch them, I'll let them go. Did you see it? Let me do it again. Are you looking for it, Maggie?
Yep.
Did you see it right there? All right, one more time. Crazy. They're zooming all around the room. Okay? They have these forces. They have energy sort of wrapped up in that configuration. So I want to know how much work does it take to move this charge over there. And I know that as I move it closer and closer, here the force is basically 0. But as I move it closer and closer, it gets a bigger and bigger force until I get it right here, and I got a really big force. So I want to figure out how much work does it take to move that charge from one position to another, and that work will be equal to the potential energy. I have this written over here. The work required to bring another charge from infinity, and that's where V equals 0, to the point P, where now V is equal to KQ over R, is equal to the change in potential energy for the charge. Now we would have to, if we wanted to look at how the force changed, we would take each step and add up the force times the distance for each little step. That would require integral calculus, right? Because that's what an integral is, that it's a sum over a certain variable. But we don't have to do that because I have this definition of potential. Potential energy is equal to Q2 times V1. Or this is based on our basic idea that potential is energy over charge. And so this is equal to Q2 K Q1 over R. That's the distance between the two. And so I can rewrite this for delta PE, and this is on your equation sheet, Q1 Q2 over R. The potential energy contained in those configuration of charges is equal to that. And if I let them go, that's how much energy is going to go into kinetic energy. Sorry, you guys can't see very well at the bottom, can you? I'll try to keep it up. We've talked about putting that back part of the classroom, like lifting it up about 3 feet. Wouldn't that be awesome? Let's see what we can do about that. All right, so if Q1 and Q2 are both positive, the potential energy is, where am I? It's positive. Work must be done to hold, I thought I took this out. let's just sort of take this out, okay, guys? It's not really that important, and it often just confuses students more. So you can, that bottom part of 30, we'll just take out. Let's just jump right to an example. I have these two charges here, and I want to know how much work was required to assemble these two charges. Another question I could ask is, what is the potential energy of these charges? And that would be the same answer. Like if I have this 3 microcoulomb charge all the way over here, I want to know how much work does it take to put it right here. So let's try this. The work, goodness bless you, is equal to the potential energy, which is equal to K Q1 Q2 over R. So that's 9 times 10 to the 9th. That's our K value. R, as I like to put it in my calculator, and I recommend that you do the same, 9E9. If you don't know how to do that, ask me. All right, Q1 is 2 times 10 to the 6th. Excuse me, negative 6. Q2 is negative 3 times 10 to the minus 6. I keep those negative signs. That's different than what we did for fields or forces, but we're talking about scalar quantities here. And then divided by R, which is 1 meter. And so that's what, 18, 30, 54, negative 54 times 10 to the minus 3, I think. Negative 0.054 volts. Okay? Now, your problem, you'll probably have one of these on your test where I give you a configuration of charges and ask you to determine, I'll either ask how much work did it take to assemble these charges, or I'll ask what is the potential energy of this configuration of charges. It'll probably look something like this, where I have 3 charges, and I want to know how much work is required to assemble the charges into this configuration. I'm going to help you out a little bit because you don't really know right now how to do this, but let me show you, and then I'll let you go forth with it. And also, let me just point out, sometimes on the older exams, I taught this slightly differently, and I talk about the work required to move one charge into each place. So like, for example, here, I would say, let's start with just the plus Q charge. How much work did it take to bring into place? And the work required to bring it into place is 0. And then I'd say, now let's move in the plus 2Q charge. And I would say, how much work is required to bring that into place? And that work will be equal to Q times delta V, where delta V is only due to that charge. And then I would say, let's bring in the plus 4Q charge. And what is the work done by it? And it's going to be Q times delta V, which will include the potential due to the 2Q charge plus the potential due to the plus Q charge. So if you see that in, like, if you go back and look at older exams, I'll approach this type of problem in that way, where I say, let's bring in this charge and ask what work is being done. And it's going to be that Q delta V. Which is, I mean, we're still doing the same thing, but you bring the charge in and you ask yourself, what is the work being done? However, I found that students, just in practice, they really sort of go back to doing it this way, where you say, these two charges, they have a certain amount of potential energy. These two charges, they have a certain amount of potential energy. And these two charges, they have a certain amount of potential energy. So I have 3 distinct pairs of charges, all of which contain a certain amount of potential energy. And so the total potential energy would be the sum of the green, red, and blue potential energies. It's the same as doing it here, but it just works out. I find students can do it a little more easily. Is that exciting for you? This is probably the least exciting part of the entire course right here. And from here on, uphill. I mean, downhill. More exciting. I don't know. It's more exciting. All right. So I would calculate this. PE is K QQ over R. PE is K QQ over R. And PE is K QQ over R. For each of those individual forces, each of those charges, those pairs of charges, and calculate then the total potential energy, which is the sum of those individual 3 energies. All right, so I'll give you all a go on that. So what you need to do is to calculate the potential energy for each set of charges. I'll never give you more than 3 charges, so there either be only 2 charges, in which there's only one set, or 3 charges when there are 3 distinct pairs of charges. Let me start your clicker base. Now, can y'all see the answer right there? I mean, I know you can't. You have it. There it is. Evan, can y'all see that sort of thing? Sort of. I'm waiting on a call.
Oh, really?
Yeah, here, leave it right there, please. All right, let's just do about 10 more seconds. Y'all doing pretty well. Ask your neighbor what they put if you want to check your answer. All right, we'll stop at 222. 222. Okay, good. A is right. So I'll just do the first one, okay? I'm just going to do this one right here. PE is KQQ over R. This is the green. PE is 9 times 10 to the 9th. That's K. Q and 2Q, that was 1 coulomb. 2 coulombs divided by the distance, which is 2 meters. And so that is 18 times 10 to the 9th. That's in joules. All right? And then you do the others for the red. I don't know what it was. Can anybody know what the red was? 1.8 times 10 to the 10th. So that's 18 times 10 to the 9th. And then the blue was
36.
all right, and then you add them all up, and you get 6.3, right? Isn't that what y'all put? Yeah, that looks right. 6.3 times 10 to the 10th. What'd y'all get on that? Yeah, take one. The green one? Oh, yes, thank you. So this should be 9 times 10 to the 9th. Is that a joke worthy? Is it 89%? Okay, let me think. Listen, don't think any less of me for telling you the Alright? What did the blanket say when it fell off the bed? Oh, shoot. Alright, y'all have a great day. I'll see you Wednesday. Oh, we probably will go into capacitance, but we'll talk about whether it's on the test on Monday or not.